In this video, we're going to talk about expanding and factoring expressions. I'm going to remind you what it means to expand or to factor, and then we'll do a few examples. When we're expanding expressions, we're using the distributive property to turn a product into a sum of two or more terms. On the screen now, you see a couple of standard examples. The first example asks us to multiply a single-term polynomial, what we call a monomial, by a three-term polynomial, what we call a trinomial. And when you multiply a monomial by a trinomial, you distribute the monomial to each term of the trinomial. The operation here is multiplication. This is what most people think of when you mention the distributive property. Multiplying each term of a multi-term polynomial by a monomial. When we perform the multiplication, we just have to use the laws of exponents. So when I take x cubed times x squared, because the bases are the same, I can add the exponents and consolidate that into x to the fifth. When I take x cubed times negative 3x, the negative 3 floats out front. It's technically being multiplied by the implied coefficient of 1. And speaking of implications, there's an implied exponent of 1 here. So when I take x cubed times x, I add those exponents and get x to the fourth. When we take x cubed times 4, we take the implied coefficient of 1 times 4, which is 4, and then the x cubed gets tacked onto the end, and we've now expanded that product. What was once written as a product is now written as a sum of terms. To expand in the second example, we would also use the distributive property, but most people don't call it that. Most people refer to this as FOIL. FOIL is an acronym for a way to keep organized when you're expanding this product. You multiply the first term in each set of parentheses, then you multiply the outer terms, then you multiply the inner terms, and then you multiply the last terms. First, outer, inner, last spells FOIL. But you can see this is just the distributive property. We multiplied the 3x by each of the two terms in the second polynomial, and we multiplied the 1 by each of the two terms in the second polynomial, and so it's just the distributive property. Let me erase my arrows here, and we'll go through each step one at a time. We do the first terms. 3x times 2x is 6x squared. Remember that there's an implied exponent of 1 on each of those. Then we do the outer terms. 3x times negative 5 is negative 15x. Then we do the inner terms. 1 times 2x is 2x. And then we do the last terms. 1 times negative 5 is negative 5. Now that we've completed the distributive step, you can see we've got some like terms in the middle. We usually want to put those together. You do not change the exponent on the variable when you add and subtract. Negative 15x plus 2x is negative 13x minus 5. And so we get our final expanded version, 6x squared minus 13x minus 5. Sometimes we're expanding a polynomial raised to a power, and in those examples for now, we're going to have to write it out in order to multiply. There are formulas that you can memorize, and in fact, there's a theorem called the binomial theorem that kind of shortens the procedure. We're going to investigate that at the end of the course. But for now, all we really know how to do is expand by using the distributive property. So I would encourage you to write out what the product means and then apply the distributive property. For example, in this first problem, the square of 5x minus 4y, I'm going to rewrite this as 5x minus 4y times 5x minus 4y. Now it's just like the previous example. I'm going to use the FOIL process. 5x times 5x is 25x squared. The 5x in the first polynomial multiplied by the negative 4y in the second polynomial would be negative 20xy. The negative 4y in the first polynomial times the 5x in the second polynomial would also be negative 20xy. And then negative 4y times negative 4y is positive 16y squared. And we collect those like terms in the center to finish it off. 25x squared minus 40xy plus 16y squared. A common mistake is to take this exponent and just apply it to each of the two terms individually. But notice that that doesn't generate this middle term that you get from actually following the procedure. So the exponent doesn't distribute to the two terms individually. Same thing in the second example. It would be awesome if all we had to do is cube the x and cube the 1 and get x cubed plus 1. But that's not what it means to cube x plus 1. To cube x plus 1 means to multiply 3 copies of x plus 1 together. Unless you know a shortcut formula or the binomial theorem, this is the only way to do this. When you multiply 3 polynomials together, you have to do something similar to what you do when you multiply 3 numbers together. If I told you to take 2 times 5 times 4, you would first multiply 2 times 5, and then multiply the result by 4. Or you could do it in another order. You're allowed to take 5 times 4 first and then multiply by 2. But the point is that you have to multiply 2 of them together first and then take that result times the third one. You wouldn't distribute the 2 to the 5 and the 4. Multiplication doesn't distribute over multiplication. So you're going to start by multiplying 2 of them together. So I'm going to take x plus 1 times x plus 1. That's x squared plus x plus 1, following the FOIL procedure. And I have to multiply that by the x plus 1 that's on the end. Before I do that multiplication, I probably want to simplify this first. So that's x squared plus 2x plus 1, when I combine the like terms in the center, times the x plus 1, the last polynomial. Now I follow the distributive property again. This isn't technically FOIL because it's a trinomial times a binomial, but you follow the same procedure. We don't give a name to this because it doesn't spell anything. You do first and then outer and then middle times first. So we have full, it's not going to spell anything. So instead of being cute about it, we're just going to call this the distributive property. I take x squared times x, that's x cubed. Then I take x squared times 1, that's x squared. Then I take 2x times x, that's 2x squared. And then I take 2x times 1, that's 2x. Then I take 1 times x, that's x. And then I take 1 times 1, that's 1. And then I collect my like terms. I get x cubed plus 3x squared plus 3x plus 1. Notice that you can't just cube each term because you get these middle terms when you actually expand the polynomial. There are shortcut formulas for raising binomials to powers. We're going to learn the binomial theorem at the end of the class. The rules for squares and cubes aren't hard to memorize, so you might choose to do that if you don't want to go through this process. For higher powers, we're going to learn this binomial theorem at the end of the course. I don't think we need to do any more examples because they're all basically the same kind of problem. But reversing this process and factoring can have a few different flavors, so we're going to spend a little more time on that. To factor a polynomial means to write it as a product of 2 or more polynomials. So we're going to take an expression which is written as a sum of terms and rewrite it as the product. Typically when we factor, we want to factor completely, which means we're unable to break down any of the polynomials in our factored form any further. Sometimes factoring really does just look like reversing the process of distributing a monomial. In an example like this, 4xy cubed z plus 18y squared z squared, you can see that the 2 terms have some common factors. Both of the coefficients are divisible by 2. Both of the terms have at least 2 copies of y. Both of the terms have at least 1 copy of z. You can almost imagine that 2y squared z being distributed through some other polynomial. We call that the greatest common factor, and we're going to start by writing that out front. 2y squared z. Now we just have to figure out what it is we would distribute that monomial to in order to get the original polynomial. And I do this as kind of a question and answer session, but it's really just a division step. You're just dividing each term by this greatest common factor in order to figure out what's left. But for whatever reason, I don't think of it that way. I do it more like a guessing game. So I say, what times 2 would give me the 4? Well, there had to be a 2 here, so that when I distribute, I get the 4. I need a copy of x, and there's no x in the GCF, so there has to be an x in the first term inside the parentheses. This had 3 copies of y, but I've only stolen 2, so I need 1 more, so that when I distribute, I wind up with a y cubed. I need a z in the first term, but that's exactly what I already factored out, so I don't need to introduce a z. If I check this, you'll see I get 4x y cubed z, exactly what the first term is. Play the same game on the second term. What times 2 would give me 18? That's 9. Notice that's just what 18 divided by 2 means. It's really just a division step. I need a y squared, but that's exactly what I pulled out. I need 2 copies of z in the last term. I've only factored out 1, so I need 1 more. Close up the parentheses, and there's our factored form. Notice that inside the parentheses, they don't share any common factors other than 1 or negative 1. 2 and 9 have no common factors. There are no common variables to each of the 2 terms. This is completely factored. We'll do a more complicated version of this in a moment. When most people think of factoring, they think of factoring like this, where you've got trinomials. In each of these examples, we're going to try to rewrite these in terms of the products of two binomials. Notice that in each example, there's no common factor among the three terms. Like looking at the first example, 7, 10, and 8 have no common factor other than 1 and -1, and the last term doesn't have an x, so we can't pull out a GCF like we did in the first example. We're left trying to come up with the product of two multi-term polynomials. The standard first attempt is to try two binomials. You might know some organized process for doing this, like an AC method or something like that, a box method. I'm going to do this by a guess and check method, and I'll try to give you some insights to what I'm thinking as I guess. In the first example, the leading term is 7x squared, so I'm going to need two terms that multiply to 7x squared, and the most obvious thing to try is 7x times x. When I start the FOIL process, that will give me the 7x squared. My focus is on the constant term next. I need to come up with an 8, but I'm keeping that 10x in mind. I need two numbers that multiply to 8, and I need to place them in such a way that when I do the outer and inner part of the FOIL process, I get that 10x. There are some guesses that you can tell are immediately wrong. Like if I put the 8 here, that's definitely going to be wrong, because when I do the O in FOIL, that's going to give me a 56x, and there's no way I'm going to get back to that 10. So there are some guesses you can immediately dispel just based on your intuition. It doesn't seem like 8 times 1 is going to work at all, but I also have 4 times 2 as an option. And my intuition tells me that the 4 can't go over here because that's going to be a 28x. So my first guess would be to put the 4 with the 7x and the 2 here. After I make my guess, I check what the outer and inner terms are going to be. I do this mentally, but hopefully you can't see into my head, so I'm going to write out what I get. 7x times 4 is 14x, and 4 times x is 4x. I see that if I do 14x minus 4x, that will give me the 10x in the middle. I need this to be a negative 4x, which means that this sign has to be a minus. I need this to be a positive 14x, so I need this sign to be a plus. Then I just double check that that gives me the right sign on the constant term, negative 4 times 2, and that gives me negative 8. At this point, I'd like you to try that second example. I'd prefer you try it by guess and check, but if you're dedicated to an organized process that you learned somewhere else, you're welcome to use it. Pause the video and give that a shot. Okay, here's my thought process. I'm going to try to break this down into the product of two binomials. That's usually your first try. My gut tells me that 8x times x isn't going to be a good idea because the middle term is so small, but there's actually an upper level reason why I know 8x times x won't work. See how the first term is even and the second term is even? The only way I'm going to get an even second term is if I break the 8 into two even numbers. If I break the 8 into an even number and an odd number, then with this odd number on the end, it's going to give me an odd term in the middle. So there's this super nerdy reason why I know the only reasonable guess is 4x times 2x. 3 is prime, and so there's only one way to break that up, 1 and 3, but I have to figure out where to put the pieces. My instinct tells me that I need to take the 3 times the 2. 3 times 4 would be 12, that's too big. So I'm going to try organizing this with a 3 and a 1. On the outside, I get 4x, and on the inside I get 6x, and if I add those together I get 10x, so these should both be positive, and you can see that gives me the positive 3 on the end. So my factored form is 4x plus 3 times 2x plus 1. For some polynomials, no matter what you guess, you just can't break them down. We call those kinds of polynomials prime, and we'll talk about how we handle those in the future. Let's try a polynomial with a higher degree. This example asks us to factor x cubed minus 16x. The first thing I look for when I factor is a greatest common factor. Not only is that a necessary step in order to factor completely, but it'll reduce the coefficients or the powers on the variable and often make your factoring easier. I'm going to pull out a factor of x. X times x squared would give me the x cubed. X times 16 would give me the 16x, minus sign in between them. The resulting binomial is called a difference of squares. The first term is a perfect square, obviously it's x squared. The second term is a perfect square, it's 4 squared. You might recall that there's a formula for factoring those. If you have the difference of two squares, you can rewrite that as the sum of the square roots times the difference of the square roots. Using that difference of squares formula, I can break down this binomial into the product of two binomials. The first term in each set of parentheses is the thing you have to square in order to get the first term. That's x. The last term in each set of parentheses is the thing you have to square in order to get the second term. That's 4. And then you alternate the signs. I typically put the plus first and the minus second, but that doesn't matter. And there's our factored form. We could have also arrived at this factored form by guess and check. The only reasonable way to get x squared in the front is to take x times x. In order to get 16 in the back, there were 3 options. There's 1 times 16, 2 times 8, and 4 times 4. But the only way that you're going to get the middle terms to cancel is if those two have the same magnitude. So 4 times 4 was the only option. And then you have to alternate the signs in order to get the negative 16. That's also why the middle terms cancel. You can do it by guess and check. I would encourage you to learn this formula, though. If you're not familiar with it, it's worth memorizing. Let's look at another higher order polynomial. This one doesn't have a GCF other than 1. And so there's nothing that we can pull out. Trying to do this by guess and check is possible, I suppose, but it would be difficult to come up with those guesses. One thing that makes this problem stand out compared to our other examples is that it has 4 terms. And one thing to try when you've got 4 terms is called factor by grouping. What I'm going to do is I'm going to just find the GCF of the first 2 terms and just find the GCF of the last 2 terms. I notice that the first 2 terms have a GCF of x squared. I can factor out an x squared. X squared times x to get x cubed, x squared times 4 to get 4x squared. And now I need to pull the GCF out of the last 2 terms. And you can see that they're both divisible by 4, but just pulling out a 4 doesn't work. When I factor out a positive 4, I get negative x minus 4 inside the parentheses. And now my progress is stalled. I have nothing else that I can do here. I'm kind of stuck. I don't have a GCF. I don't see any obvious way to factor this. So pulling out a positive 4 doesn't work. However, if we pull out a negative 4, then the binomial that we get is another x plus 4. Negative 4 times x would give me the negative 4x. Negative 4 times positive 4 gives me negative 16. And now I can proceed because I have a greatest common factor. I have a common factor of x plus 4. And you can pull that out just like you can pull out any other GCF. I'm going to pull x plus 4 out of the whole thing. When I pull x plus 4 from the first term, it leaves behind an x squared. And when I pull x plus 4 from the last term, it leaves behind a minus 4. And now that's a difference of squares. That's that a squared minus b squared form that we saw on the last page. That factors to a plus b, a minus b. See if you can break that down on your own. Hopefully you were able to do it. What do I have to square to get the first term? Well, x. What do I have to square to get the last term? 2. And then you alternate the signs, 1 plus and 1 minus. And now we have the factored form of this polynomial. When you factor by grouping, it's important that the polynomials that you create from that match. If they don't, then you can't proceed because there's nothing to factor out. You can only pull out common factors, and so if those 2 factors aren't the same, then factor by grouping has failed and you have to try something else. Either reorder the terms and try factor by grouping again, or maybe that process won't work at all. We'll see examples later on in this course where factoring by grouping will not work and we have to try something else. Okay, we're ready to ratchet it up a bit. In this example, we're asked to factor the cube of 6x minus 5 times 2 times x squared plus 4 times 2x plus the square of x squared plus 4 times 3 times the square of 6x minus 5 times 6. Whew! And this problem looks made up and just mean. But you actually see things like this in calculus. When you do these problems that combine these 2 processes called the chain rule and the product rule, you wind up with polynomials like this. And after you do the calculus and you come up with this, you have to factor it. So that's what we're going to do. The first thing I would do is clean up these expressions a little bit by seeing if there's anything that I could combine. So I'm going to look at each term individually and see if there are any monomials that I can multiply together. For example, in this first term, I can take 2 times 2x, and that's 4x. I would do that first. Everything else I would just copy down. The 6x minus 5 cubed, the x squared plus 4. Copy those onto the end, the 4x floating out front. I'm going to do the same thing in the second term. I see 2 monomials, 3 and 6. I can multiply those together to get 18. X squared plus 4 squared, 6x minus 5 squared. We haven't achieved a whole lot with that, but it is a little bit cleaner. It makes it easier for me to identify what the greatest common factor is. That's the next step. I'm going to look for common factors among the 2 terms. There are only two terms here, everything to the left of this plus sign and everything to the right of this plus sign. So I'm looking at these two terms. In the monomials that we just created, the common factor is 2. I can't pull an x out of this second term because there isn't an x over here. I see that there are copies of 6x minus 5. How many of those do we have? Well, there are 3 in the first term and there are 2 in the second term, so I can only pull out 2. I can pull out a 6x minus 5 squared. And then I see there's an x squared plus 4 in each term, but there's only 1 in the first term, so I can only factor out 1. If this feels vaguely familiar, it's because it's exactly like the problem that we did here. We pulled out 2 copies of y, because the second term only had 2 to give, and we pulled out 1 copy of z, because there was only 1 copy to give. I did the exact same thing here. After pulling out the 2, we pulled out 2 copies of 6x minus 5, because the second term only had 2 to give, and we pulled out 1 copy of x squared plus 4, because the first term only had 1 to give. Now we can't stop there. In this example, we had to come up with the other expression. This isn't equal to the original expression. I have to multiply all of that by something. So I'm going to come up with that something, and again, I'm going to do that with my guessing technique. What times 2 to get the 4x? Well, 2x. What would I have to multiply 6x minus 5 squared by in order to get 6x minus 5 cubed? Well, I'd need 1 copy of 6x minus 5. There's an x squared plus 4 here, but that's exactly what we took, so we're good there. Plus, what times 2 to get the 18? 9. There are 2 copies of 6x minus 5, but that's exactly what we took, so I don't need any of those. There are 2 copies of x squared plus 4. We took 1. We need 1 more. Again, exactly like what we did here. No different. Harder, but not any different. This is factored at this point, but we usually simplify this to see if we can go any further. So we'll do that quickly here. I use the distributive property here to get 12x squared minus 10x. I use the distributive property here to get 9x squared plus 36. And now we collect the like terms inside that set of parentheses, copying down all the rest of this stuff. And we get 21x squared minus 10x plus 36. This turns out doesn't factor, and so we're done. If this did break down further, we would do so. I promise you that it does not, so we're done. When you look at that wall of work, this seems complicated, but I want you to recognize that it's just like this problem. It's very similar. I want you to think of it as a problem like that and do the exact same thing. Now we're going to dive into some examples that aren't polynomials. The concepts are exactly the same, but people will often freak out when they run into these examples for the first time because they're not used to working with negative exponents or fractional exponents when they're factoring. But don't change any of the ideas. When we pulled out the GCF in both that previous example and the easier example, let me pull up the easier example, we pulled out the greatest common factor of the coefficients, and then we found the smaller of the exponents in each case. So there were 3 y's here, there were 2 y's here, so we pulled out a y squared because that's the smaller of the 2 exponents. There was 1 z here, there were 2 z's here, so we pulled out 1 because that's the smaller of the 2 exponents. We really even did that with the x's. There's 1 x here, but there were 0 x's in the second term, so we didn't pull out any x's, we pulled out 0. We're going to do the exact same thing here. In the first example, we have 15x squared y to the negative 3 minus 15x cubed y to the negative 4. I'm going to start by looking for the numerical GCF, which I think you can see is 15. They both share 15. Then I'm going to go to the x's, and this doesn't seem difficult because we have positive exponents on each. There are 2 x's here, there are 3 x's there. We take the smaller amount, right? We take 2. Now we're going to play the same game on the y. Even though these exponents are negative, we still apply the same rule. We're going to take the smaller of the 2 exponents and pull that out. The smaller number between negative 3 and negative 4 is negative 4. So that's what we're going to factor out. Now we have to ask ourselves, what do we multiply by in order to get the original polynomial? The first term has a 15. Well, we've already pulled out the 15. It had 2 copies of x. Well, we've already pulled out 2 copies of x. It has a y to the negative 3, and we have a y to the negative 4. What would I have to multiply by y to the negative 4 in order to get y to the negative 3? Well, I'd need one copy of y so that when I add the exponents, I get negative 3. Negative 4 plus 1 is negative 3. Now I play the same game in the back, although this will be easier to see. There's a minus sign, I already wrote that. 15, I already pulled that out. There were 3 copies of x, I only took 2, so that leaves 1 behind. This was a y to the negative 4, but that's exactly what we stole, and there's our factored form. Let's go through the logic one more time and describe how we got each of the pieces. The numerical part of the GCF is pretty easy. They both had 15, so we pulled that out. With the x's, this is old school factoring. There are 2 x's here, there are 3 x's here. We can only pull out 2. It's the smaller amount. With the y's, we also want to pull out the smaller exponent. Negative 4 is smaller than negative 3, and that's why we pulled out a y to the negative 4. I figure out what's left over by just asking what do I have to multiply the GCF by in order to get each of my pieces. But there are other ways to think about it. For example, you can really just subtract the exponents. This is obvious with the x's. There were 3 x's here, we took out 2, and 3 minus 2 is 1, and that's why there was an x to the first left over. I can do the same thing with the y's. In this first term, there was a y to the negative 3, but I pulled out a negative 4, so I could subtract those. But negative 3 minus negative 4 is also 1, so there was 1 copy of y left over. It's the exact same idea. One beautiful thing about this is if you're not sure if your answer is right, you can just distribute and make sure you get the original expression. If you're not convinced that this is correct, go ahead and distribute it and see if we get what we started with. The second example has fractions instead of negative numbers, but the concept is the same. You might even find this easier because there aren't any negatives. Start with the numerical part of the GCF. Both 35 and 72 are divisible by 7. Here's the weird part. I've got an x to the 2/3 and an x to the 5/3. Well, 2/3 is definitely the smaller of the two. And then with the y's, we've got y squared and y to the first. We want to pull out the smaller of those two. There's my GCF. Now I ask myself, what would I multiply that GCF by in order to get each term? So 7 times 5 would give me the 35. There's an x to the 2/3. That's exactly what we pulled out. I don't need to mess with that. I need to take y times y in order to get y squared. In the back, 7 times 6 to get the 42. And now here's the weird part. I ask myself, what do I multiply x to the 2/3 by in order to get x to the 5/3? Students tend to find this harder to do because of the fraction arithmetic, and that's where this subtraction step might come in handy. Instead of asking it as a guessing game like I like to do, just subtract the exponents. You're starting with a 5/3 and you pulled out a 2/3, so subtract those. That's 3/3, which is 1. It leaves behind an x to the first. There was a y there, but we stole it, and there's our answer. Again, if you're not sure, you can distribute and check that. The only part really in question is we really get that 5/3, I suppose. But if you take 2/3 and add 1, that's 2/3 plus 3/3, which is 5/3, so it'll work. All right, here we go. This example not only has fractional exponents, but actually has a fractional negative exponent, so probably can't get much worse than this. And again, this might look like it was made up just to be torturous, but this is in fact the result of a calculus step. The first thing we're going to do here is that bookkeeping step where we find the monomials and multiply them together in each term. There are only 2 terms here. There's this term to the left of this plus sign and the term to the right. So in the first term, I have 2 monomials. 2 times 4, that's 8. And then everything else I'm just going to copy down. Didn't do anything with the 3x plus 2 to the 1/3. Didn't do anything with the 4x minus 5. In the second term, there's actually a nice result. 1/3 times 3 is 1. When 2 things multiply to 1, we say they cancel. And so in the second term, we just copy down what's left over after we cancel. 4x minus 5 squared and 3x plus 2 to the negative 2/3. Now we're looking to factor here. And so we're looking for common factors in the 2 terms. The 8 has nobody to play with over here. We can't pull out any numbers here because the coefficients on the right canceled away, remember? So we don't have to do anything with the 8. With the 3x plus 2, we've got a 1/3 power and a negative 2/3 power. Remember the rule. As ugly as that looks, the rule is take the smaller of the 2. Negative numbers are always smaller than positive numbers, so I'm going to factor out that smaller exponent, negative 2/3. The 4x minus 5s are a little more straightforward. There's one copy of 4x minus 5 on the left. There are two copies of 4x minus 5 on the right. I can only pull out one. Now I ask myself, what's left over? Well, there's an 8 left over in the first term. And here's the hard part. You can do this my way by asking what you would multiply 3x plus 2 to the negative 2/3 by in order to get 3x plus 2 to the 1/3. But I found that many people are much more comfortable doing that subtraction step that I showed you before. Start with the one that you were given and subtract what you're factoring out. You're guaranteed to get a positive result every time you do this because you've always factored out the smaller exponent. Here this turns into plus positive. We get 3/3, which is again 1. So that's a 3x plus 2 to the first. Don't need to write the exponent, it's implied. Plus, no coefficient on the back here, so I don't need to worry about that. There were two copies of 4x minus 5. We took one. There's one left behind. There was also a 3x plus 2 to the negative 2/3, but that's exactly what we stole. I'm going to copy this stuff down again and simplify inside the brackets. Forgot to finish the brackets, sorry about that. In the first term, I can distribute, get 24x plus 16. In the back, there's nothing to distribute, so 4x minus 5. And now I just collect the like terms just to check to make sure there's nothing I can factor out. 24 plus 4 is 28, so that's 28x. 16 minus 5 is positive 11. 28 and 11 have no common factors, and so we've taken this as far as we can. And I know when you look at this slide, it looks awful. But if you just take it one line at a time, it's really not that bad. There are two difficult parts. You have to get used to finding the smaller exponent, even if it's a fraction or a negative number. And figuring out what's left over can be tricky, but if you remember to think of it as a subtraction step, it's not that bad. You'll definitely want to practice examples like this, so make sure you dig some up to try. Make sure you take some time to practice some of the stuff that you've already seen before too, especially the factoring of trinomials, because that comes up a lot. If you have any questions for me, you can find me in an office hour or shoot me an email.